home tab. Okay, you click, so this home page will come it out. Now in the center you see there are virtual labs of different subjects. So ours is physical science, so you click on that, and in physical sciences also there are multiple subcategories, subtopics. So you need to go in this time you need to go to this solid state physics virtual lab, which is there, which is at the second last number. So you have to go to the solid state physics lab. Under this you can find out this Hall effect experiment. Okay, so you click on that. Okay, so this web page will come out. Hall effect experiment again. Those who are doing first time, they may not see this particular screen, not this one, but simulator part. Let's discuss that also later on. But coming to this, you see on the top there are few tabs: theory, procedure, self-evaluation, simulator, assignment, reference, and feedback. Okay, so one by one you have to go through this. So first is the theory tab. Okay, under this you can find out very important details about the experiment like aim. So let me annotate also, so you people maybe have clear idea. So you see this aim. So aim is very important. So whatever the experiment you perform, not only from the physics side, but any practical, you must know the aim of that experiment. That means what exactly you want to do in that practical. So in this practical, we have two aims. One, to determine the, you see first one, to determine the Hall voltage developed across the sample material. And the second is to calculate the Hall coefficient and the charge carrier concentration of the sample material. So all these technical term which you are seeing over here, Hall voltage, Hall coefficient, charge carrier concentration, everything we'll discuss later on. So first, these are the two aims which we are going to follow in this practical. And then coming to the operators required, you see over here. So all such components which we require to perform this experiment, they are listed over here. You can easily go through that. And same way you can identify also from the simulator part, okay, whether these components are really existing in the simulator or no, or they just for fun purpose they have provided over here. Of course it is not the case, but it is your task to verify whether all such components are there existing in the setup or no. Okay, then coming out to the theory. Okay, so this theory usually I told many times that when you write into the word file or into the manual notebook, this theory part you don't need to write it. Okay, but to understand the experiment you must go through the theory part, then only your fundamentals about the practical may be clear. Okay, so let me explain it little bit. This part you have to cover it from your side, but let me explain it little bit about this. So this coming to this first, what is Hall effect then? Okay, since the experiment name is the Hall effect. So what is Hall effect? So when a current carrying conductor, okay, it is placed in a perpendicular magnetic field, then what may happen? Because of placing into the perpendicular magnetic field, a voltage difference may arise across the conductor. Okay, and that voltage difference will create the electric field, and that electric field will be perpendicular to both current as well as magnetic field. So for example, if you consider, let's say if current you consider along x-axis, and then if you place that current carrying conductor in a perpendicular magnetic field, and let's say magnetic field is along y-axis, then your electric field will be generated in the perpendicular to both, that means along the z-axis. Okay, so that's what this experiment is. So this effect we are knowing as Hall effect. The voltage which difference which you are getting, okay, that voltage we are knowing as a Hall voltage. And there is a coefficient also, Hall coefficient. So that formula is also there to calculate the value of Hall coefficient. Let me show you that also. Here is the diagram. Okay, that all xyz directions are given, and with this diagram if you go through it carefully after reading the theory, then you can immediately come to know that what happens actually in this diagram. Okay, what will be the purpose of this diagram. Okay, so this part I am leaving to you, but I have given you the brief idea about this Hall effect. What is that? Okay, all such components they have given what they are representing. And if you go further, okay, they have derived the formula for Hall coefficient also. So they have given the formula of this Hall coefficient also derived also. So if you people are interested, then you can just check it out how they have derived. Otherwise, our purpose over here is to calculate the Hall effect parameters. Okay, so I am not going much into the theory part, but otherwise it's very simple. You can see it out. There are two forces which they have equaled it: electric force and this magnetic force, which you see this one. Okay, and then later on they put various values of different factors, and then come out with the final formula. Okay, so it's very simple to understand. You can go through it. It's not a problem. But I am coming directly to the formula which we are going to use in this case. So that is this one, RH. RH is the Hall coefficient. VH is the, you see this VH. This VH is the Hall voltage. There is a T, this one. So this T is the thickness of the sample. Then you see the capital I in the denominator. That I is the, let me remove it out all. Okay. So this I, this one, I into B. So this I is the current. Okay. And this B is the magnetic field. Okay. So that's why you get this value of RH by calculating this formula. And this formula will give you the value of RH in SI unit. Now again, there are few other notes or content in which the value of RH is different. They have multiplied with the factor of 10 raised to 7 because they have converted this scale into the CGS scale. So right now we are using the SI unit, so don't need to write or multiply with any factor. But if you are using the CGS system, then of course you can see one more additional factor, that is 10 raised to 7 in product. Okay, so it is up to you, whichever way you want to prefer, CGS or SI, but SI is preferable generally. Okay, and again if you come down below, then there is another parameter or another formula is there, RH equal to 1 upon Ne. What is N? N is the charge carriers, number of charge carriers. E is the charge of electron. Okay, so with this formula, if you know the value of RH, you can calculate the number of charge carriers available in the sample material. So right now with this virtual experiment, we are finding these two components. One is the Hall coefficient RH, and the second is the charge carriers, number of charge carriers. And number of charge carriers depend on the type of material. If it is semiconductor, then you see number of holes may be there, number of electrons may be there. But if it is a metal, then number of charge carriers will be electrons only. Okay, so depending on the material, you can decide how many number of charge particles are there. Okay, so that number you can calculate it out. So this is the theory part. Okay, so you go through it properly, you will come to know important things. Then you go to the procedure. Now again in procedure, you see they have given all such details regarding the simulator part, whatever the components they are using. So combo box is there, button, slider. You just go through it once so that it will be easy to understand in the simulator. But again, I will also explain it to you people, no doubt. And then important thing, you see this procedure for doing the simulation over here. Okay, so there are so actually to perform this experiment is basically in two steps. You need to go first, you need to measure the magnetic field, okay, and respective current. That means current and magnetic field only you have to note it down in first step, and in the second step you have to perform the actual practical. Okay, so just keep in mind this practical we are performing in two steps. In the first step we are noting down the magnetic field and the current. In the second step we are noting down the other Hall effect parameters. Okay, so for both such process steps they have given these all such details, how to perform it, how which parameter or which button you need to press something. All such details they have given in the procedure part. You can go through it, and then you see the table also, right? So for first step, this is the table which we are following, that means current and magnetic field. So these two only you have to record it into the first process. And in the second process, as I said, it is all about the Hall effect related parameters. So in the second step, again they have given the steps for the second process, and this is the table they are following for the second step. Okay, so you can note it down or you can copy paste it into the Word file, whatever way you like. So these two things we are following, but again I'm repeating you, both the process you need to do one by one. So first, always the first process, and in the second this Hall effect process you need to do. And at the same time they have given the procedure for doing real lab also. So almost similar, whatever you do on the virtual platform, almost similar steps we are following in the offline level, so real level. So okay, so there is not much difference. If you have clearly completed this experiment, then you are able to do the same thing in real level. So, and at the last, you see the result part they have given. So result Hall coefficient of the material. Okay, right now they haven't written the unit, but as I told you earlier also, physics is not complete until you place the proper unit. Okay, so Hall coefficient, the unit is meter cube per coulomb. If you are following the CGS unit, then that is centimeter cube per coulomb. Okay, so depending on the CGS or SI, you decide the unit. And charge carriers always we are finding out in per unit volume. So that is why you see this charge carriers is in meter cube, meter inverse cube, or per meter cube also you can say. So because we are finding out charge carriers per unit volume. So these two results you need to write it down after completing the experiment. So this is how this procedure part is done. So that's why I told one by one you go to the theory tab, then procedure tab. Now coming to the self evaluation. So if you have gone through the theory and procedure properly, then you must be able to answer all such MCQs. Okay, so depending on your understanding after going through the theory and procedure, you can select the correct answer. Okay, which one is the correct? You choose it. Okay, there may be 4 to 5 MCQs, and then you select and submit it. To just checking, it is like a pre-test, so that you can so that you can understand how much you have understood the practical. Okay, and then coming to the fourth tab, that is the simulator. So those who are doing the first time, for them it may be difficult to see this screen. Okay, because again there is an error message will come out based on the browser. So many times it is giving the problem of the flash player, so you need to install it. Okay, if it is not there, if it is install it, then you need to allow it. So it will asking the message like run Adobe Flash Player. So you just click on the button. It will guide you, so you don't need to worry. Okay, it will guide you what steps you need to take. You can perform it that, and after that, after installing or after enabling, you must see this screen. If still it is not possible, then you try to restart your browser also after installing everything. Again, the problem is if you are facing the same problem still, then you can try out in Internet Explorer, because some of you the users have said that they are easily opening it in Internet Explorer rather than Chrome or Mozilla or something. Okay, so you just try it out. If it is not working in one browser, then you can open in the another browser also. Try to open in that. Okay, so since I am using Mozilla Firefox, it is perfectly working fine in my system. You see this setup will come out on the screen. Let me move it further. Yeah, so now it is the Hall effect. Okay, so first we are going to cover the first process. So if you see on the left hand side this diagram, this setup will be there. Okay, so let me first identify the component. Here is the solenoid which they were talking in the operators required. So there are two parts, or generally people are saying is poles also, first pole, second pole, whatever, and in between there is a gap. You can see that this much is the gap between these two poles. Okay, and this is your emitter, which is displaying the current in ampere scale, and this is your this one is your Gauss meter, which is displaying the value of magnetic field in Gauss. And this one is your probe. Okay, that you need to insert between the solenoid, okay, between these poles, so that then only you can measure the magnetic field between these. Okay, now because you know very well, if you are passing the current through the solenoid, then magnetic field is going to be generated along that. So then you have to place this probe over here and note it down from this Gauss meter. Okay, so let me clear it out all such stuff. Okay, now coming to the practical side. So you see on the right hand side pane, select procedure. So there is a drop down. There are two things, but again, as I said, first you need to go for the first step, that is magnetic field versus current. You click on that. Then you need to click on this button, insert probe. So you see the moment I click on this insert probe button, you see there is a change in this wooden stand. Okay, so now you see this, that probe has come out at this wooden stand. Okay, now there is a message on the screen, click on the wood. So somewhere at any moment, any point, you can click on the wood. So this particular wood stand will insert it, I mean this probe will be inserted in between the poles, just like in the diagram. Okay, and the moment you have inserted, now you have to vary the current to the solenoid. Okay, so now I am varying the current which is going to the solenoid. So there is a slider, so you can move it, and the slider is moving with the interval of 0.5. So 1, 1.5, 2, 2.5, 3, 3.5, something reading you can take it out up to 5 ampere. So let me drag it little, 1.5, and as you can see this emitter is also changing on this picture. Okay, as well as you see the reading in the Gauss meter also. The moment I change the current again, you see both emitter as well as this Gauss meter. Gauss meter is more important because emitter already you can see I am changing the current from the slider. Okay, so you see then, okay, 2 ampere again it got changed, 2.5 again it got changed, 3, 3.5, 4, something, and like that you can go on. Okay, so what you have to do is you have to note down, you change the current and corresponding magnetic field reading from the Gauss meter, you have to note it down in the table number 1 as you have seen in the procedure. Okay, so in the table 1 you have to note down the current which you are changing, and according to the current how much magnetic field is generated, that you have to note it down from this Gauss meter. Now obviously it is clear that if you are increasing the current, that means this magnetic field strength is also getting increased. Okay, once again you can check it out and see 1 ampere it is around 0.1482. If you move it further, you see magnetic field is getting increased. Okay, so this is what you are getting. You just note it down all such result into the table number 1, and that's it. This is only the first process up to this moment. You cannot do anything with silicon material thickness or Hall current. You are not able to do anything because it is disabled at this moment for this first process. So now after completing this, after noting it down into the table, you need to go for the second step, that is Hall effect setup. Now you see the arrangement slightly changed, that probe has changed to some different unit. Okay, and at the center somewhere you see I will use this pointer at this moment, this one here we are keeping your sample, semiconductor or it may be metal, that material sample we are keeping at this dot you can see on the red color which I made. So at this moment between these 4 terminals we are keeping your sample material. Okay, fine. So this probe now we are going to insert over here just like in the same case. Okay, so you have selected this Hall effect setup, insert Hall probe. You see probe has come up to this wooden stand. Now there is a message on the screen, click on the wood. So you click anywhere on the wooden stand. So this has inserted in between the solenoid. Okay, and now again this current will be there. So what you have to do is whatever the current value you have taken in the first set, same current value you have to set it. Suppose you have set it 1 ampere. Suppose you have taken 4 readings, 1 ampere, 2 ampere, 3 ampere and 4 ampere. Then at first you have to select it 1 ampere and don't change it further. Okay, what you have to change is the remaining quantities. Okay, so keep it at 1 ampere only. Then you select your material. There are few metals and 1 semiconductor. So whichever metal or semiconductor you like, you can select it out. Germanium is the pure semiconductor. Apart from other 3, these are the metals. So whichever way, so that's why this practical is valid for both germanium as well as valid for semiconductor as well as metals also. Okay, so you select any one, let's say germanium only, and then I have shown you the sample which is there at the center on the probe. Okay, so that sample thickness also you can change it from this dragger, the slider. Okay, so whatever the thickness you want to keep, you just keep it and don't need to change further. Okay, so that means you need to keep the fixed thickness. So between this 0.0001 to 0.0009, any thickness you can keep it whichever you like, but after selecting don't change further, just fix it, that's it. Okay, so let's say I'm keeping this thickness, fine. And then now whatever the sample, as I said, sample is in probe. Okay, at the center I have shown you earlier. So now you have to supply the current to that sample which is there in the probe. Okay, so that current we are knowing as a Hall current. Okay, and that Hall current you need to vary. Again you see the range, it is in milliampere. Okay, so there are 2 currents we are following. One current which is in the ampere range, that we are giving to the solenoid. Okay, then only it will generate that much amount of magnetic field. between the poles, and the second current which is in milliampere, and that we are going to give to the semiconductor or metal sample only. Fine. So here is the range 1, and again it is varying with the interval of 0.5. So after 1, 1.5, 2, 3, 2.5, 2, 3, 3.5, 4, 4.55, you can take the value of Hall current. So this part again I am repeating, current to the solenoid, that is 1 ampere, you keep it fixed. Material, you keep it fixed once you decided. Thickness also you need to select at a particular value and keep it fixed, don't need to change further. But this Hall current you need to take at different level. So suppose at 1 milliampere is the Hall current, then you click on the button show voltage, so it will display the voltage on the same, you see current and voltage you can see on the same device, so it will show you the voltage. Again you go to the current, move it little bit, 1.5, again you click on the button show voltage, note it down, then again coming to the current, move it further. So that's how you can take 4 to 5 readings over here of Hall current. So again I am repeating, for 1 ampere current which is given to the solenoid, you may take 4 to 5 readings of Hall current and corresponding voltage by clicking on the button. Okay, and this all such details you can note it down over here in the table. Okay, thickness of the film which you have decided just now, so you write the thickness whatever be the number, let's say 0.0001 or something, whichever number you have decided or fixed, you number you provide over here. Hall current 1, 1.5, whatever, you note it down. Hall voltage also you have seen, so one by one you can note it down over here. Gauss meter reading you have to take from the previous table, whatever that, and then you click on this result part. Okay, so it will show you the Hall coefficient, and that result you can write it down over here in this, either this one, and then this charge carriers also you can write into the last column over here. Okay, and after taking one reading you click on this button save. Okay, and further readings you can click on the plus button, so that multiple table entries will be generated and you can write down the further readings. Okay, and save it every time, and at the last you can export into the Excel file, or you can export to the PDF also, or directly you can copy paste also into the Word file, whichever way you like you can do that. Fine. So this is how you can perform this particular experiment. Again keep in mind, once you decided this particular sample, don't need to change thickness also, you don't need to change, only thing is you need to change the Hall current. Okay, so suppose again if you have taken 1 ampere current which is given to the solenoid, 4 or 5 readings of Hall current and Hall voltage has been recorded. In the next set, now change the current to the solenoid again, let's make it 2 ampere, keep the material and thickness same, but Hall current again you vary from 1 milliampere to the, I mean you mean to take 4 to 5 readings again for Hall current and Hall voltage. Same way again in the third set, change the current to the 3 ampere. Okay, and keep all such material and thicknesses same, but Hall current and these values you take again 4 to 5 times. So like this you may have 3 to 4 sets of readings, and then you can find out the value of RH from that. Okay, I have given you the PDF, in that also you can see that. So I'm expecting that now this experiment is very clear to you people. Okay, so after completing this you can go to the assignment. Okay, and see if any of the activities, if you are able to complete it. Okay, so go through that, and then you go to the reference tab. So here they have given the references of all such books or papers whatever they have referred in this practical, and apart from that they have given the bibliography also. Okay, so few links, hyperlinks are given over here, so you just click it out and check it out the content, so that will also clear more doubts whatever you may have during the practicals. So the doubts may be clear by you following these links.